the important thing to know here, that machine learning is just a method of data analysis that automates analytical modeling. It's closely coupled to a field which is often be called data science, and there's also some people that like to describe themselves as data engineers. Same thing as normal science and engineering. Um, Engineering just a little bit more applied, right? So within the field of artificial intelligence, this is going to be the highest level of everything that you're doing, right? Trying to make things that think for themselves. Artificial intelligence kind of as a field came about in the 70s, but you can make decision makers, you can make if then statements, logic machines, but it was really hard to pre-program all of that. So then people said, well, what if I don't have to program it? What if I can just train a machine to program itself? And that's what machine learning is. So machine learning is the next step down. That's the automated development of methodologies. So linear regression is a machine learning tool, because you're not individually figuring out how to draw a line through data. You have a mathematical framework that draws a line through data. Now, if you go to a conference and say, I'm going to talk to you about my machine learning algorithm, and you pull out linear regression, people will make fun of you. But I would objectively say that you are technically correct, and technically correct is my favorite type of correct, but you won't win any awards. And then about 2014, a new field came out, which was deep learning. Deep learning is taking multiple layers of a neural network. So neural networks had been around since the 80s. People had hypothesized them, tried them, but they were just too hard to train. And some very smart people figured out that you could use these GPUs that were being used for gaming, and you could train neural networks in parallel. Neural networks mathematically are not the best solution for a lot of this, but because they can be trained in parallel, they're computationally efficient to train, right? So neural networks and deep learning became a big field kind of circa 2014. Data science is what pulls all of what ties some of the machine learning and AI with our core engineering disciplines, right? Because we are an engineering group. So if you think about what you know as an engineer that no one else is going to know, and what you should, lean into your strengths of, right? So you know more about sensing. You know that there's no such thing as a digital sensor, right? Digital is just a way that we communicate data. You know that the only thing that we can measure is voltage. No one can measure current or resistance, right? You get current and resistance by just measuring a voltage drop over a resistor. So lean into your strength. You're very good at data acquisition, very good at domain expertise, right? Finite element models, you know that, 100 pounds of force is not a big deal, like in a house, right? You know that 10,000 pounds is a heavy load. And, some people who are not in engineering might not be able to actually just kind of conceptually see that. Then if you think back to your undergrad, right, we had some statistics, which is a core competency here of data science. And then big data is just a lot of data. When the data is too big to kind of fit in the memory on your hard drive, that's when we're talking about big data, visualization, data preparation, edge computing. These are all things more in the data science realm than the engineering realm, but things that you can pull from. And so that kind of shows how we can merge the machine learning with our core engineering, right? So one thing that I like to say is that ML, is not building robots, right? We're not doing controls. Machine learning is just focusing on the algorithms that can learn from and make predictions or decisions based on data. That's all machine learning is. So we're going to bring into that, dive into that a little bit deeper. The spam filter was like for emails, was one of the initial uses for machine learning, right? And one of the most common applications. It classifies emails as spam or ham, I guess. Ham is what you want, spam is what you don't, which I actually find slightly offensive as someone from northern Iowa, southern Minnesota, where spam comes from. I think that was on needed, but that's okay. Um, so another good technology that came out of machine learning, right, was speech to text. So speech to text technology kind of converted spoken language into written text, with used kind of in virtual assistants. That kind of is what started us. We've been working for a long time on building these advanced chatbots that we now have with generative AI. And generative AI would be a field within deep learning, right? So of course we have to add another one there in the future. Also trying to do more machine learning with like medical diagnostics. We're not, this machine learning is not of itself making decisions. It's just using algorithms to classify or regress information from data and do it automatically. So machine learning has a lot of jargon. Oh, sorry. JARGON. So machine learning has a lot of jargon, and one of the things we want people to come away with from this class is just an idea of what the jargon is. Whenever someone says, "Oh, that's a buzzword," maybe it is a buzzword, or maybe it's just they don't want to spend the time to figure out what's going on with it. But when you are at a company and someone comes to sell you a product, you want to be able to ask some questions back, right? Because people will drop a first term, then as soon as you ask a question back and they don't have an answer, then you might want to think a little bit about spending money with that firm or buying something. Some of the big ones here that we'll go over, we're going to go over these more in detail later, are supervised, versus unsupervised learning. And so supervised learning involves training a model on labeled data, and unsupervised involves training a model on data with no labels, right? And trying to find hidden patterns. So a label is something that you put on something, right? If you've got a tub of containers, you'll put a label on something. This is apples, this is oranges. That would be supervised learning. If you just give the machine learning apples and oranges and you don't tell it which is which, it's going to just try to figure out that these two things are separate, but it won't know that one's an apple, that one's an orange. It just knows that they're different. We have online versus batch training. And online training is an algorithm that updates a model incrementally, and batch training is an algorithm that takes in all of the data and then tries to process the data. Batch training can be more efficient, but sometimes you have too much data, right? Your computer has a limited amount of memory. You'll hear us talking about that a lot in this class. And so online data means I can bring in a little bit of data at a time, and my computer can handle that. Batch training means I can bring it all in. Sometimes it might be more efficient, but I have to have the memory to enable that. And we can also do instance versus model-based learning. So instance-based learning algorithms, right? K nearest neighbors. They use a specified instance to make a prediction. So they're just kind of pulling straight from the data from the instances. Whereas model-based algorithms like linear regression, they'll build a model and then they'll use that model to make a prediction. If you're ever trying to extrapolate out past the end of your data, which is always something really dangerous to do, model-based approaches are better, right? So you can have a model that extends out past the end of your known data. Instances can be very good at classification, and instance-based learning can be very effective. So one of the things that we can look at here is 1.1 examples of AI. All right, so let's take a look at AI. So artificial intelligence, right? This is going to encompass a very diverse array of technologies and methodologies. And is also going to include all of our machine learning, our deep learning, and our generative AI as a field, right? So one of the earliest things that we did with AI was we tried to build expert systems. Right, and this is a very logical idea. This is the idea that what you do is you get an expert. He's an expert, or they are an expert because they have glasses and a pocket protector. That's what an expert looks like in my mind. And you ask them a bunch of questions, right? So this might be a doctor, it might be a carpenter, it might be a plumber. And you start to put all that information into a knowledge base. And then from your knowledge base, you're going to have an inference engine. If this, then that, right? If your toe hurts, you should probably stop kicking it. So, and then you might have some non-expert users that make a request. They get a user interface, and then you get some advice back. This has been a very common way to do expert systems for the last 40 years. So that's kind of a very basic way to do an expert system. This has more recently been replaced by chatbots, right? Which instead of explicitly bringing information in and building a knowledge base, right? You're building representations of knowledge in some sort of vector or transformation space. This is much closer to what like ChatGPT and Llama are doing. So, yeah.
Would this be considered a supervised learning framework? There's a expert feeding the knowledge. Like, is that like?
You could consider it that. I mean, when we talk about supervised and unsupervised, we're typically talking more about machine learning, and there's going to be some aspects of that here. But yeah, sure, yes.
Also, is he an expert because he doesn't smile?
Yes, because he knows too much. They know too much. The expert knows too much. So, all right. One of the earliest forms of an expert system actually is something that I find really interesting. Not the earliest forms, but we used to build custom hardware for expert systems. And here, this Symbolics Lisp machine, and it was specialized hardware to run expert systems and a version of AI focusing on answering questions, right, to challenging problems. The idea was that you would put this in the corner of a factory floor, and someone could come in and type in their questions. What bolt should I use here? What nut should I use here? And then this machine would provide you an answer. It never really worked, and kind of the whole field never really worked. And so there was something that people like to term as like the AI winter, right? They put these out on shop floors. Boeing bought some, and then no one used them, and everyone kind of gave up on AI for a long time until deep learning came around and kind of started to replace things. So within within AI, right, we can look at some examples of machine learning. And so here, you might have linear regression. Right, so that's just going to be your basic statistical method for modeling the relationships between a dependent and a variable. And then you can have classification. Right, and that technique, it's more of a decision tree or support vector machine that categorize data into predefined classes like apples and oranges or cars and trucks, that type of thing. And then you can also have some simple image / speech recognition. And we can use some simple machine learning vision tools to say classify digits, right? Like the post office does for mail, or some very basic speech recognition, all without getting into deep learning. Right. So, however, the machine learning works well, particularly if it's well-constrained task, and that's what we're going to focus on the first half of this class. But we also want to look at kind of some examples of deep learning. Right, so deep learning, right, it's just an enhancement to machine learning, and it utilizes deep neural networks, which really just means neural networks of more than 3 or 4 layers. Now that seems super trivial because you can train it on your laptop, but even just in 2010, you could, 2010, 2014, you were not training, multi-layer networks on your laptop. So these were originally conceptualized in the 70s and kind of really initially unfeasible due to some of the vanishing gradient problems in the network. So in 2012, a gentleman named Jeffrey Hinton and team demonstrated that a network with 60 million parameters and 650,000 neurons could effectively perform image classification on a data set of about 1,000 images. They introduced some really cool things here, including dropout and things of that nature, and really demonstrated that deep learning could do image classification. So,
elaborate on the vanishing gradient problem. Why is it bad? Why do we avoid it?
when you're training back through a network, you have a gradient. Oh, here, let's do this. All right, so when you have a simple neural network, you're going to have one layer, and a deep neural network, you're going to have multiple layers. At each one of these nodes, you're going to have some amount of gradient that you're trying to train across, right? And that's how you update your weights. And as you move back, you're going to put the most emphasis on training the gradients at the end of the network, and the gradients at the beginning of the network aren't going to get as much attention, right?
So the deeper the network, the more the gradient.
The more that the gradient can, yeah. And it just takes more and more data to train it. So that was the challenge, and it's not very efficient to train, and it takes a long time. So if you can crack that using neural networks, using GPUs, then you can do better image classification. So these are results from a competition that happened every year. And they would give you 1,000 images, and then your job was to show up and classify it, right? And you were getting relatively, kind of winning errors of 27%, 25%, and it wasn't really improving a lot year on year. And then when AlexNet showed up with Jeffrey Hinton's team from the University of Toronto, you dropped over 10%, right? And so that was all based on deep learning. And about 2012, right, just a year later, all of a sudden everyone had image recognition on their Facebook pages, right? It's like, oh, this is this person, this is that person. And that was all enabled by this deep learning, and just kicked off a huge acceleration and development of GPUs, and led to NVIDIA being one of the reasons NVIDIA is the company that they are today. NVIDIA was also the first to kind of bring out a programming methodology to allow you to program their GPUs for doing this type of work. So this was a pretty groundbreaking paper. We don't say that a lot, or maybe we do. But it's really a paper that made a big improvement here in the field of machine learning. So ImageNet classification using deep convolutional neural networks. We call it AlexNet. Geoffrey Hinton got a Nobel Prize for it in physics. Is it physics? Maybe, maybe not. But and then the poor middle author always gets forgotten about. So, but I'm sure they're all doing fine right now. And so actually, last year in 2024, Geoffrey Hinton got a Nobel Prize. So on the left here, this is John Hopfield, and then this is Geoffrey Hinton, and then this is the King of Sweden. And then this lady, I don't know who she is, but she read a very good kind of description of the work, and then they come up and get their prize, shake hands with the king says something, and they go and they sit down. Wonderful award ceremony, because they didn't let the professors talk, which I thought was very nice. And I was fortunate enough to get to go, and so I actually took those pictures.